Hi, we're here to talk about migration and its effects on a population's genotypic and allelic frequencies. So what is migration and how does it affect population? Migration is when a group of individuals from one separate population with different genetic frequencies moves to another population and intermates. Migration is a violation of what is called the Hardy-Weinberg equilibrium law. The Hardy-Weinberg equilibrium law consists of 4 assumptions: infinitely large population, random mating, no selection, and no migration. And migration is a clear violation of this equilibrium law. How does migration affect genetic variation? Well, there's 2 ways in which population migration can do this, and that's either between populations or within populations. So say you have this population of brown squirrels at NC State, and you have this population of brown and gray squirrels in North Raleigh. And these 2 gray squirrels decide, hey, I'm going to migrate to NC State. So they migrate over to NC State. How does their migration affect the genetic variation between the populations? Well, it decreases it because now the populations are more similar to each other. How does it change the population at NC State? Well, before these gray squirrels came to state, there were only brown squirrels, so there wasn't very much genetic variation. But when they migrated over, it increased the genetic variation within the population because now there's both brown and gray squirrels. One equation you will use frequently to solve migration problems, and it's built off the concept that the change in gene frequency depends on the immigration rate and the gene frequency in the immigrants. So the variables that make up this equation are P prime, which is the frequency of the allele you're looking for. Then there's M, which is equal to migration rate. Now migration rate is the proportion of migrants after immigration has occurred. Then you have little p, which is the frequency of the allele in the non-migrating population. Lastly, you have big P, which is the frequency of the allele in the migrating population. Now it's important that you keep little p and big P straight because it can be easy to confuse them. So what do these variables look like put together? Well, the equation is P prime, the frequency you're looking for, is equal to 1 minus m being the migration rate, times little p plus m times big P.
So here's an example problem. Suppose there are 80 squirrels on the NC State campus with brown and gray coat colors. The brown coat color is dominant, meaning that it can either have a big B genotype or a big B genotype. The gray coat color is recessive, so it can only have the little b genotype. The frequency of the big B allele on the NC State campus is 0.7. The frequency of the big B allele in the nearby neighborhood is 0.5. 20 squirrels from the nearby neighborhood decide to migrate to the NC State campus. Now, what is the allelic and genotypic frequencies of the new population after one round of random mating? I will show you how to do the allelic frequencies first. Using the formula, we must find the different variables in the problem. Little p and big P are given to us within the problem. The frequency of the big B allele in the campus population is 0.7. we'll be using this for little p. Now the frequency of the big B in the migrating population is 0.5. We'll be using that for the big P. Now, the only other variable we don't know is M. To figure this out, we must take the number of squirrels migrating into the population, which is 20, and divide it by how many squirrels are in the total population after migration, which would be 20 plus 80. So the value of M equals 0.2. Now that we know what numbers to plug into the equation, we can solve for P prime. So P prime equals 1 minus 0.2 times 0.7 plus 0.2 times 0.5. Once this is all worked out, you get that P prime is equal to 0.66. This means that the frequency of the big B allele is equal to 0.66. Now that we have the frequency of the big B allele, finding the frequency of the little b allele should be easy, because the frequency of the big B allele plus the frequency of the little b allele should equal 1. So to find that, we do 1 minus 0.66 and get that the frequency of the little b allele is 0.34. So the frequency of the big B allele again is 0.66, and the frequency of the little b allele is 0.34. And now you have the allelic frequencies for this problem.
After finding the allelic frequencies, the next step in this problem is finding the genotypic frequency. One definition of a population is its genotypic frequency. This frequency gives an indication of the genotypes that are the most and least prevalent in a population. So at first, we had a population of the NCSU campus that the most prevalent gene was the brown coat color. After migration from the nearby neighborhood of 20 squirrels into the NCSU campus, the prevalence of the brown coat color gene is going to change. So, in order to find the genotypic frequencies in this problem, a couple conditions have to prevail in each situation that you were to solve for genotypic frequencies. These three conditions are: the population has to be able to mate randomly for one generation, there can be no further immigration, and there can be no other violations of the Hardy-Weinberg equilibrium. These three conditions must be met in order for one to find the genotypic frequency of a problem. There's an important equation that you will need to know in order to figure out your genotypic frequencies. And this equation is P squared, which allows you to find the following terms of finding your homozygous dominant alleles. Next, you have 2PQ, which defines your heterozygous dominant. And then you have Q squared, which defines your little b, your homozygous recessive. This following equation helps you find all your genotypic frequencies. Now that we have gone over a couple conditions of genotypic frequency and gone over the major equation that we need to solve for a genotypic frequency, let's go ahead and solve for them. So after you calculated your allelic frequency, it is quite simple to find your genotypic frequencies. As you learned before and calculated these new allelic frequencies for this new population, your big B, or your frequency of your big B, which also equals big P, equals 0.66. Your frequency of your little b, which in this case equals Q, equals 0.34. I will describe to you how to individually get the values of the homozygous dominant, heterozygous, and homozygous recessive frequencies. Then I will show you a common way to check your answer. So let's find your homozygous dominant frequency. First, you have to determine what frequency one would use. In this case, we would use the frequency of the big B allele, which is 0.66, which also equals our big P. We would then square this value to get the genotypic value of the homozygous dominant. This will look like the following. P squared equals 0.66 squared. Once we do the math on this problem, this will give us a value of 0.4356. So, the genotypic frequency of the big B in the new population is 0.4356. So now that we know the new frequency of the big allele homozygous, we must find the heterozygous genotypic frequency. In this case, we will use both allelic frequencies, P and Q, and you will plug in your frequency into the equation 2PQ. So it will be 2 times 0.66 times 0.34. So this will look like this. 2 times 0.66 times 0.34. This will give us a value of 0.4488. And this will be our frequency of our big B, little b genotype. So overall, the genotypic value of the heterozygous genotype is 0.4488. The reason that you use both allelic frequencies in this case is because one is trying to use a big allele and then a small allele within the genotype. For the next frequency, we will find the frequency of the homozygous recessive genotype. In this case, we will only need to use your Q allelic frequency. So now we will solve for our homozygous recessive, which will be Q squared. So to solve for this, you would take 0.34 squared. This will give us a value of 0.1156. This is the new homozygous genotypic frequency. So the frequency of the little b genotype is 0.1156. After solving for each genotype, overall we got a new genotypic frequency of 0.4356 big B plus 0.4488 big B plus 0.1156 little b. This is of the new population after one round of random mating has occurred. I will now explain a good way to check your answer. First, you take both of your allelic frequencies and plug them into the equation that we use to find your genotypic frequencies, which is of the following: P squared plus 2PQ plus Q squared. So that will look like 0.66 squared plus 2 times 0.66 times 0.34 plus 0.34 squared. So a great way to check is to see if this equals 1. And in this case, this does equal 1. So in this case, we correctly solved for our genotypic frequencies.
After viewing this video, we hope that you understand migration and population genetics. Overall, migration is when a group of individuals from one separate population with different genetic frequencies moves to another population and intermates. Migration is a violation of the Hardy-Weinberg equilibrium law. It is an extremely important topic in regards to genetics. This concept allows the prediction of genotypes for new populations of individuals and is essential for the genetics world. Thank you for watching. This video was made by Megan Parker, Alana Harvey, and Sumana Goli. Here's a list of references, and we'd like to thank Dr. Gardner for this opportunity. Thank you.